So welcome everyone for the second session on this lectures on quasi-isometry invariants. So during the first session, I had explained how, given a finitely generating group with a finite generating set, we could associate a metric space. We could see the group as a metric space. So first by looking at the word metric that counts the minimum number of words of letters that you need to express an element of the group with the generating elements. And then we associated the word distance between two groups. And from that, we defined the Kelly graph, okay, whose set of vertices was the whole group G, and the edges had the form G times S, where G is an element of G and S an element of the generating set. Okay, so today what I would like to understand is in which respect does the generating set influence the geometry of this metric space that we obtain with the Kelly graph. Okay, so the first remark that I will leave as an exercise is that if S and S primes are two finite generating sets, then the word matrix ds and ds prime are bi-Lipschitz. So this means that there is some constant L, so at least one, such that for any elements x, y in my group G, if I look at the distance with respect to S prime, then it is bounded from above by L times the distance from x to y, and bounded from below by the distance from x to y with respect to the other generating set. Okay, so this is a nice property being bi-Lipschitz. It's used very commonly in analysis. The thing is that if I look at the Kelly graphs, we've seen that even for the simplest groups, such as the cyclic group Z, depending on the generating set, the graphs were far from being isomorphic. When I had taken the genetic set plus n minus 1 or plus 2 n minus minus 3. Okay, so etc. Okay, so then it means that seems that looking at a Kelly graph will make a it's not a canonical choice, and so this can cause us some trouble if we want really to understand what's going on. And so the next, what I would like to do now is to explain a statement that is called that some people call the fundamental lemma of geometry group theory, that will explain what is the relationship between the different Kelly graphs that we can obtain for a given group. And so for this, actually, I will go to a broader setting and consider what are called the geometric action. Okay, so I let X, it is a metric space. Actually, I will assume that it is proper and geodesic. So what does it mean? So proper means that closed balls of finite radius are compact. So typically, this means that, for instance, Rn is a proper metric space. So every closed and bounded set is compact. So it's not always true. For instance, in infinite binary spaces, it is not the case, infinite dimensional binary. So this is a way of taming a little bit the space. And geodesic means that between 2 points, I always have a curve, the length of which is exactly the distance. So this means that for any xy, there is an isometric embedding f from the segment zero to the distance xy to my set x, such that f of 0 is x, and f of the distance from x to y is y. Of course, I could have done the opposite, but it doesn't make any difference. Okay, so this is proper and this is geodesic. Okay, and so now I will consider specific actions. So what is a geometric action? So group the action, if let G act on X, so it is geometric, the action is geometric. If, so first it is an action every G acts by isometries. Okay, so this means that distances are preserved. Second, I want the action to be properly discontinuous. So this means that given two compact sets, subsets, KL in X, if I count the number of elements G such that when I translate K by G, it intersects L, then I want this to be finite. And the third condition is that the action is co-compact. And so what does it mean? It means that there exists a compact set in X such that the set of translates covers X. That G of K. So this is the union over all the elements of the group is the whole set X. Okay, so this is a geometric action. Okay, so three properties. First, that it acts by isometries, but it was also what I was looking at in the first lecture. That it acts properly discontinuously. So this is the fact that only finitely many elements can make compact sets intersect. And the third is that the action is co-compact, meaning that we cover the whole space just by looking at the translate of one compact. Okay, so the fundamental lemma. So let's talk about the fundamental lemma of geometric group. Yeah, which is U independently. Okay, so it's Schwartz and Milnor. So Schwartz, sometimes it's written like this. That's a long story that I won't tell, but either way is okay. So let G act geometrically on a proper geodesic metric space X, then first G is finitely generated. And second, given any finite generating set S, there are constants lambda at least 1 and C positive, such that what I want to do is to compare the distance given by the orbit map on X and the world distance, or the distance in the Kelly graph. So what does it say? It says that if I look at the distance in X, and here I take for any G1, G2, and G. If I look at the image between the distance between the image of X by G1 or G2, then it is bounded from above by lambda times the world distance between G1 and G2 up to a constant C, and it is at least 1 over lambda, the distance from G1 to G2, minus C. So this is the first property. And the second is to say that the image is co-bounded. So meaning that if I look at the union over all the groups, all the elements of the group of the ball centered at G of X and of radius C, then it covers the whole space. Okay? So let me just comment a little bit the statement. So we have a geometric property saying that we have a special action of a group on a metric space. So this is the geometric action. And then we conclude with an algebraic property saying that the group G is finitely generated. And not only that, what we also know is that we can compare the distance along the orbit map with the world distance for any finite generating set. In particular, this also applies for Kelly graphs. So if I take one group, what you can check is that the action of a group on its Kelly graph is always geometric. This was the drawing I had done with the wedge of circles. And so this means that if you look at two Kelly graphs, I can compare them with this. And this is where the notion of quasi-isometry comes from. So maybe before proving the theorem, that is very important, so I want to give the proof, I would like to define what is a quasi-isometry. So it's really inspired by this statement. So the definition, I think it appears first in a paper of Margolis from 70 or 71. A very short paper in which he improves a little bit Mostow's rigidity theorem. Okay, so a quasi-isometry. First, quasi-isometric embedding is a map F between two metric spaces such that there are constants lambda and C, such that the distance in Y between f of x and f of x prime is at most lambda, the distance, lambda times the distance from x to x prime up to C, and at least 1 over lambda, the distance in x, from x to x prime minus C. Okay? And quasi-isometry is a quasi-isometric embedding such that the image is co-bounded in Y, meaning that if I look at the union over all points in X of the ball centered at f of X of radius C, it covers the whole set Y. So it is almost onto. So what you can see is that this definition is really that property that I have written down. Okay, so what is kind of weird the first time that we see this is the fact that we have this additive constant. So a quasi-isometry need not be continuous. Actually, the most interesting ones are not. So this is the case when you want to compare two different Cayley graphs, like the ones I've shown with the cyclic group Z. In each case, the Cayley graphs are different, but we know that they are the same on the set of vertices up to bi-Lipschitz equivalence. And to take into account the fact that the edges are different in the graphs, then we use this constant C. And the second comment that I would like to make is that if the distance from X to X prime is very big, then the influence of this constant C disappears. So it means that at large distance, the map F looks like a bi-Lipschitz mapping. Okay? And so this is the whole strategy coming from this theory of geometric group theory, of looking at groups like geometric objects, is that we look at them up to some little local error, and this error is fixed, is encoded into this constant C. And so what does the lemma says? It says that the orbit map the image G maps to G of X is a quasi-isometry. Okay. And so the corollary would be to say that two locally finite Cayley graphs of a given group are quasi-isometry. So they are quasi-isometric means that there exists a quasi-isometry between one space to the other. Okay, so here it's even better because the quasi-isometry is equivariant, meaning that it commutes with the action of the group. But otherwise, we don't need that. You see, the notion just comes from metric space. So let's prove the lemma. Okay, so I have to use the fact that I have a geometric action. So first, I let K be a compact set such that its orbit covers the whole set. Okay, so I let D be 3 times the diameter of K plus 1. So this means that for any X in X, there exists some element G such that G of K is inside the open ball centered at X and of radius D over 3. Okay. So here I use the fact that the action is co-compact to say that. Okay. And now I want to define, find a finite generating set. So I will let S will be the set of elements G in G. So I fix a base point, W and X, such that G of W is contained in the ball of radius centered at W and of radius D. I forgot if it's that or not. So because the action is properly discontinuous, this means that S is a finite set. Okay, because W is a compact space because it's just a singleton. And here what I could do is just close it. It won't make any difference. If G of W is inside the ball, then it is also in its closures. So then I can apply directly the definition that I have already erased. Okay, and now what I want to check, let us prove that S generates a whole group. So this means that I have to prove that any element of my group G can be written as a product of elements of my set S. Okay, so for this, I have W here. So I pick G and G, an element of my group. I look at the image of W by my element, so I get somewhere on G of W. And then I know that my space is geodesic. So I can look at the segment, the image of the segment of length, the distance from W to G of W inside my space X. So the idea is the following. You subdivide the segment into pieces of length D over 3. Okay, so you can do that until you get too close to the endpoint. And here maybe it's very small, but it's smaller than D over 3. Okay? So this means that, so I have my curve gamma from 0 D of W to X. So this is the curve in white. I fix a subdivision T0 equals 0, T1, T2, up to Tn equals to the distance from W to its image. Okay, such that the distance of two consecutive points, Tg plus 1, is equal to D over 3. Okay? So this is the distance in my space X. Okay, so far so good. So here I have, for instance, gamma of Tj. Here I have gamma of Tj plus 1. And so this is gamma of Tn minus 1. No, it's not here, it's there. Okay. And so now, what do I say? So I want to use the fact that I didn't pick D arbitrarily, randomly. And so the thing is that what I said is that I had picked G so that I always have a translate of my fundamental domain in the ball of centered at X of distance D over 3. So this means that what I know is that in the neighborhood of one of these points, there always exists a translate of G of W that is not too far from the point. So for any J between 0 and n, I can find an element of my group Gj of G such that the distance between gamma of Tj and the image of W under my element Gj is at most d over 3. Actually, I can even say it's strictly smaller than d over 3 because I assume that it was inside the open ball over there. So this means that here somewhere I have Gj plus 1 of W. Here I have Gj of W. And the distance there is at most d over 3 each time. Okay, we won't see anything yet. Okay, and of course I choose G0 to be the identity and Gn to be G because I can really fall on it on the top. So let's see what's going on around here. So I will make the drawing a little bigger. So here I have gamma of Tj. Here I have gamma of Tj plus 1. Somewhere, so this distance is d over 3. Somewhere not too far, I have Gj of W. And somewhere not too far here, I have Gj plus 1 of W. So what I'm interested in is understanding the distance between those two. Okay? So I look at the distance between Gj of W and Gj plus 1 of W. And I will use the triangle inequality, saying that I can control it using the 2 points in my segment. So this is smaller than the distance from Gj of W to gamma of Tj, plus the distance from gamma of Tj to gamma of Tj plus 1, plus the distance from gamma of Tj plus 1 to Gj plus 1 of W. Okay? And so this, I know it is strictly less than d over 3. This is exactly d over 3 unless I'm at the end of the segment, where it will be smaller. And here, so let's say it is smaller or equal to. And this one is also at most d over 3. What I get here is that this distance is at most d. Okay? Thus, if I compute the distance from W to Gj plus 1, Gj inverse composed with Gj plus 1 of W, because my action is by isometry, this is the same isometric action as the distance from Gj of W to Gj plus 1 of W, and this is at most d. So this means, by definition, that this element belongs to S. Because it's moving W at most distance d. And so now I'm happy. Why is it the case? Because I have my element G. G, I remind you that it is Gn. And so what I want to do is to say that the distance between these two things, it will be bounded by the sum of the distances between all these elements. So I write it the following way. First, I make G0, that is the identity, so I don't care. Then I have G0 inverse G1 times G1 inverse G2. And in the end, I have Gn minus 1 Gn inverse times Gn. Oops, it doesn't work. It's normal. Got mixed up, sorry. Okay. So I can write my element G like that. So here G0 is the identity, so it does nothing. This one belongs to S, this one belongs to S, and they all belong to S. So what I've managed to do is to take a random element G and I wrote it as a product of elements of S. So this means exactly that S generates G, and so G is finitely generated because I said that S was a finite because it was properly discontinuous. Okay? And not only that, but I also have a bound on the word distance between for G. What I can say here, I needed how many elements? Well, n actually. So the norm of G with respect to my generating set S is at most n. Okay? So that's interesting. So now I have to see that I have a control between the distances. So how does it work? I want to find a... So I want to compare the distance from W to G of W with respect to my norm GS here. So I start with the distance of W to G of W. So by definition here I have a geodesic. So I can decompose this distance into a sum of distances with midpoints. So this is equal to the sum of from j equals to 0 to n minus 1 of the distances of gamma tj to gamma tj plus 1. So this is because it is geodesic. Okay, so the problem here is that, so here it's n minus 1 because when I add to j plus 1 it makes n, is that I don't understand what's going on here, so I will forget it. So I say that this is at least the same sum where I stop at n minus 2. Okay. And this is exactly, so how many terms do I have since I start from 0? I have n minus 1 terms. And each of these distances, I know it, is d over 3. Okay. And you know that n is an upper bound for the distance for the word metric of G. So this is at least G times, so I will write it like that, d over 3 times G of S minus d over 3. Okay, so here what I proved is that distance of W to G of W is at least this. So here I have the lower bound in my quasi-isometric definition of a quasi-isometric. And now for the upper bound, it's even easier than that. So I have a finite generating set. So what I can I consider M to be the maximum of the distances from W to S of W, where S goes over my finite set S. Okay, so this is a constant, well-defined constant that is positive. Okay. And so now I want to understand an upper bound for this. So G, write G as a product S1 to Sk, where K now is exactly the norm of G with respect to my generating set S. And so what I claim is that the distance from W to G of W by the triangle inequality, it will be smaller than the distance from W to S1 of W plus the distance from S1 of W to S1, S2 of W plus the distance from S1, S2 of W to S1, S2, S3 to W, plus etc. And in the end, what I get is the distance from S1 up to Sk minus 1 of W, and then up to G of W. I should write it down like the other. So S1 up to Sk of W. Okay, and so now the trick is the following. My group acts by isometries. So here I have S1 on the left is both times. So then I can, this distance, if I compose these points by the inverse of S1, this is exactly the distance from W to S2 of W. Now here I have S1, S2 on the left that are in common. So again, this is the same as the distance from W to S3 of W, and so on. And so here in the end, I have S1, Sk minus 1, that is an isometry. Here I have S1, Sk minus 1 just there. And so I can simplify because it is an isometry, and what I obtain is the distance from W to Sk of W. So what did I gain is that each of these distances is bounded from above by M. Okay? So this turns out to be smaller than M times how many terms do I have? Well, I have K terms, so this is exactly G times S. Okay? So I have an upper bound also for the distance from W to G of W. So this proves that taking the orbit map is already a quasi-isometric embedding. And now I have to check that it is co-bounded. But the fact that it is co-bounded comes just because I already know that the action is co-compact. So there is nothing else to be done. So now, I cheated a little bit because the way I stated the theorem said for any x, I have uniform bounds. So here I picked a special point W. But the same argument, the compactness argument will tell you that you can get rid of that dependence. And then, and so then this will complete the proof in this case. So you see, I've used all the assumptions. So the fact that it was co-compact enabled me to find a good size where to look at the space, the metric space. The fact that it was properly discontinuous told me that the set S was finite. And then I used the fact that it was geodesic to be able to get to this situation that I used several times. And acting by an isometry, the fact that we had an action by an isometry, I used plenty of time. Okay, so this is the end of the proof. And so this leads us to many interesting questions, because it tells us that maybe the right way to look at groups as metric spaces is to look at them up to quasi-isometries. Okay, so let me give the outshot of what we've been doing up to now. So we start with a group G that is finitely generated. To this, we can look at a bunch of Cayley graphs. Okay, they are all different. But what does the Schwarz-Milnor lemma tell us? All these Cayley graphs are quasi-isometric one another. Okay, so it means that if we want to prove a property of the group by looking at its action on its Cayley graph, then it has to be an action that is, it has to be a property that is invariant under quasi-isometries. So this leads us to the definition of saying that a property, oops, I lost my chalk. A property is geometric if it is invariant, a property of a group, okay, if it is invariant under quasi-isometries. Okay. And so what does it mean? It means that if a property P, if P holds for GS and GS is quasi-isometric to G prime S prime, then P holds also holds for G prime S prime. Okay? So in particular, I can let G prime equals to G and change S to S prime. Okay? And then we would obtain a property of the group, because it does not depend on the Cayley graph we've chosen, to the finite generating set we've chosen. Okay, so what we say is that a space is quasi-isometric to a group, to a finitely generated group, if it is quasi-isometric to any locally finite Cayley graph of the group. Okay, and two finitely generated groups are quasi-isometric if they are Cayley graphs, locally finite Cayley graphs. Are quasi-isometric. Okay, so what are the questions? So determine which properties, are geometric. That's not a question mark. It's not a question, it's a problem. What can we say? What can be said about two quasi-isometric groups? So a property that is invariant by quasi-isometries is a quasi-isometry invariant. So this ties up with the title of the course. And then, do I have another question? Well, I guess these are the two main problems that arise from this approach. And so this is what will be done. So maybe I can give some examples or results that are known in this direction. And then I will stop there for this session. So I'd just like to illustrate the second point. Because I won't have time to explain much more during these lectures. So I would like to show that there exist some very strong results. So theorem, this one is due to startings, I guess. I will go off. And so let n be at least one, and assume that G is quasi-isometric to Zn. Okay. So what can I say about G? Then the result is that then G contains a finite index subgroup isomorphic to Zn with the same n. So this means that the situation, once you understand the quasi-isometric class of Zn, then all the groups that looks like Zn, so this is what means to be quasi-isometric to Zn, means that the Cayley graphs at big scales look very close. You cannot make any difference if you take off your glasses. And then actually it contains a finite index subgroup, so this is something very light that is exactly like Zn. So essentially the quasi-isometric class of Zn only contains Zns. So this is what is called quasi-isometric rigidity for the abelian group. So the proof, I hope I'll have time to sketch it for n equals 1, but for a higher dimension, it's a very hard theorem. And there is another result in the same vein. So this is due, I guess, to Stalins, where I replace Zn by 3 groups. So let n at least 1, and assume, I will write it a little short. I will be a little more efficient. So any group, any finitely generated group, quasi-isometric to Fn contains a finite index subgroup isomorphic to the free group over n elements. Okay, maybe a small remark is that all free groups over finite alphabets are quasi-isometric. Note that this is not the case for the abelian groups, where they are not, if n is different from m, then they won't be quasi-isometric. So these are exercises that you will see. Okay, so for today, for this session, I will stop. And next time, I will try to give you some basic properties that are geometric. So thank you for your attention, and see you soon.